So now that we've described what the orbitals look like, the shapes of the s, p, and d orbitals, and now that we've also thought about the energies, right, the sizes of orbitals and things like that, what we can do now is think about specific elements in the periodic table and how the periodic table relates to everything that we've been discussing in terms of quantum numbers and orbitals and what electron waves and all of this. This is now starting to make it a little bit more practical and starts to help us understand why certain elements behave similarly and are in the same rows and columns in the periodic table. Let's start with the simplest element, hydrogen. We know that hydrogen has one electron. In fact, I'll just do this real quick right here. I've got a periodic table here. This is ptable.com. I like this website a lot. But right, hydrogen here has an atomic number of 1, which means it has one electron. So let's think about what's going to happen with that one electron. What sort of orbital is that one electron going to be in? So to decide this for hydrogen as well as all the other elements of the periodic table, there's two basic principles. This is called a building up principle, or in German, you'll sometimes see this written as the German term that was originally developed called the Aufbau principle. Building up principle, which is that we put electrons, there's sort of two rules we follow. One, we put electrons in the lowest energy orbitals. All right, and the reason for that is just that things want to go to the lowest energy. So, systems or, stuff in nature tends to go to its lowest potential energy. And so those electrons are going to want to be in the lowest energy available. And our second rule that we're going to follow is that we can put 2 electrons in each orbital. Now, why can we put 2 electrons in each orbital, and only 2 electrons in each orbital? That's because of the Pauli exclusion principle, which states that no 2 electrons in the same atom can have the same quantum numbers. So an orbital is designated by its value of n, l, and m sub l, and so the only quantum number that's left is n sub s, and that can have either plus a half or minus a half, and those are our 2 electrons. We can have the up electron and the down electron in terms of the electron spin, and those are the only 2 possibilities. So that is our 2 electrons per orbital. That's where that comes from. Okay, with hydrogen we only have 1 electron, so there's not much to worry about here. So what is our lowest energy orbital? Well, energy depends on the value of s, or the value of n. So it's going to go in our n equals 1 orbital, and there's only one possible value for n equals 1. It's L equals 0, m sub L equals 0. This is our 1s orbital. All right, and so we can put 1 electron in a 1s orbital. And so the way we'll often depict this is we'll draw a little box to represent an orbital, label underneath with 1s, and we can put up and down arrows like this or this. These represent our electrons, and the up or down represents the different values for the spin. So for hydrogen, it doesn't matter whether it's up or down, so we can just pick whatever we want. We'll say spin up. Another way this is also represented is that we can say for hydrogen, it has an electron configuration. This is what we call these, electron configuration. Let me write that down. We would write this as 1s with a superscript 1. And that tells us in the 1s orbital we have 1 electron. Okay, so that's pretty straightforward. Now let's look at helium. That's our next element that has 2 electrons. The next one on the periodic table right here. So all the way over on the other side. First of our noble gases, atomic number of 2. It's got 2 electrons. So if we follow our rules here, we're going to have our 1s orbital. Again, draw a little box for it. For helium, we have two electrons. Well, we can fit 2 electrons in an orbital, so we can put 1 spin up and 1 spin down. And that is the electron configuration of helium. Or we could write it that the electron configuration of helium has 2 electrons in the 1s orbital. Okay, but now we've filled that one up. So when we go to lithium, again, coming back to the periodic table, lithium is our 3rd element in the periodic table with atomic number of 3. we can no longer use the 1s orbital. It's already full. The first 2 electrons for lithium go into that 1s orbital. So if we look at lithium with 3 electrons, we're still going to have these 2 electrons in our 1s orbital, but now it's full. We can't put another one in because of the Pauli exclusion principle. So our next lowest energy orbital is the 2s orbital, and so we get 1 electron there. And again, we could write that as well, 1s1, 2s1. Now, why wouldn't we use the 2p orbital? Well, the order of the energies is that 2s is lower in energy than 2p. And the reason for this is that the 2s electrons have this little, we were looking at this radial distribution function. I'll draw a different color for the 2p. This isn't quite, exactly to scale, but it gets the right idea across. Our 2s electron can get a little bit closer to the nucleus because of this small part that's closer to the nucleus, and that lowers its energy. If the negative electron can interact with the positive nucleus, that will lead to a lower potential energy. And so a 2s orbital will have a lower energy than a 2p orbital. And let me write this correctly. That should be a 2, not a 1. So our electrons first go into the 2s orbital rather than the 2p orbital. And so as we keep going, that's not what I was trying to do. Thought I clicked on that. All right, as we keep going to our next element, we're going to keep filling up that 2s orbital. So beryllium is our next element that has 4 electrons. We're again going to have our 1s orbital is full, and our 2s orbital will now also be full. We finished filling that 2s orbital. And then we can move on to boron, which has 5 electrons. Again, I'll come back to the periodic table, double check that I got this right, but 1 electron here, 2, 3, 4, and we've gone over to boron, which has 5 electrons. And we're going to fill up our 1s orbital. We're going to fill up our 2s orbital. And so the next spot it's going to go is the only other n equals 2 orbital is 2p. And here I'm going to draw 3 boxes to represent our 2p orbitals. Because remember, there are 3 different p orbitals, and we can put 2 electrons into each of those. And so we would put a spin up to represent. I should draw these boxes a little bit bigger. We put a spin up electron to represent putting 1 electron into there. Let me make these boxes bigger, and I'm just going to put them all together like this. All right, so these are our 2p orbitals. Again, we have the px, py, and pz orbitals. So we're going to continue this trend. So boron with 5 electrons, and then we move on to carbon, which has 6 electrons. Again, our 1s and 2s orbitals get filled up with 2 electrons each. And now we're going to have our 2p orbitals, and we put 1 electron in each of these. All right, so I'm going to pause the video here. We'll start talking about why did I put the electrons in different orbitals and a few other things as we keep building up these electrons. And we'll look in the next video as well as hopefully you're starting to see how is this corresponding to what we observe in the periodic table as well. But I'll make that more explicit.